Hey guys, it is Mr. Van Low, and this is my YouTube channel. Do not click subscribe. Uh, okay, so today we're going to take a look at topic 3.2, in which we model a gas. So, first one, question number 41. You will need one simple formula to answer all questions of this nature, and it is this. N is equal to the mass of substance divided by the molar mass of a substance. Now, the molar mass of a substance can be easily obtained from the periodic table, as you will recall from chemistry. However, in IB physics, you are not given a periodic table. So, that is a little bit problematic. So, generally, you should assume that you will be given molar masses in a table or in the problem itself. So this is our mass, and this is our molar mass. Again, easy to calculate, but you need information that you're not given. Okay, now this ratio then is equal to another ratio, and this is in your data booklet, where we have the number of particles of a substance, and that value is divided then by Avogadro's number, which I like to call Avogad's. There we go. Avogadro's number also in your data booklet. Okay, so if you know this equation, you can handle all questions of this nature as long as you know the molar mass, which, again, will probably be given to you. All right, from that point then, and I'm not going to go through all of this rather boring algebra, all of these questions become fairly easy as long as you know these molar masses, okay? So, if you would like to pause the video and have a look at the algebra, please feel free to do so. All right, next up, 43. If the density of air in a classroom is 1.3 kilograms per meter cubed, what is the total mass of gas in a room with those dimensions? Okay, so here we have a fairly simple conversion. Always remember that we heart density. And if you don't believe me, take a look. Ta-da. We heart density. Okay, obviously, mass divided by volume. So from here, mass is equal to 1.3 kilograms per meter cubed times the volume of our room. We simply get that by multiplying all the dimensions together. And that will give us 200 kilograms. Now, for part B, we have a couple of possible approaches here, including potentially looking at the molar mass of air. I've taken a slightly different approach, and what I found is that my answer here does not agree with the textbook. And the reason for that is because this density of air is for quite a cold classroom. Okay, this classroom would not be at room temperature with this particular density of air. So the answer given in the textbook is 6,700 moles, but my answer is slightly different, and it's because I'm using the correct temperature for air that is too dense. Okay, so in any case, here we just take our ideal gas law equation and slightly rearrange it. Note that I've had to make some assumptions here. First, I had to assume that the temperature is 298 Kelvin. And if you would like to pause the video now and consider where that assumption came from, please feel free. That, of course, is room temperature. Okay, volume, fairly straightforward. One thing that is not given in the problem is our pressure. and of course we're looking at atmospheric pressure. For atmospheric pressure, it is reasonable to assume that it will be about 1.01 times 10 to the 5 pascals. Be aware that a pascal is simply a Newton per meter squared. Okay, so that's all that is. And note that if you know the unit, you now know the formula for pressure, because a Newton is a force, meters squared, area. Okay, so pressure equals force divided by area, as we have seen in prior lessons. Okay, once we've calculated the number of moles, we simply multiply that value by Avogadro's number to determine the number of molecules. And again, you would get that formula by slightly rearranging this equation, where number of molecules is simply equal to the number of moles times Avogadro's number again. Okay, obviously you're going to have a different answer if you use the molar mass, which would give about 7,000 moles. Okay, but that would also be at 0 degrees, probably. Okay, anyway, moving on. Number 45. What mass contains 2.7 times 10 to the 24 molecules? Mass of oxygen, of course. Here I've done it in 2 steps, but this is actually unnecessary. This is a fairly old, I think, version of these solutions. If I had used this equation and rearranged it, I could have done this all in one easy step. However, it's never a bad idea to show some intermediate calculations. So here there are a couple. So first, I calculate the number of moles, and I find that I have 4.49 moles. Then I need the molar mass of oxygen, and recall that oxygen gas is always diatomic, which means apply the atomic mass of oxygen by 2, giving us 32 grams per mole. So then our mass will be equal to our molar mass times the number of moles, and that's going to give us 144 grams to 2 significant figures. Note that this 32 would actually have more sig figs, but I rounded off a bit early. Again, this is probably an older solution handout, so I should probably fix it. Huh? Okay, number 46. What volume of gas contains 0.78 moles of gas at 264 Kelvin at atmospheric pressure 1 times 10 to the 5th pascals? Note that this value is slightly different than what I used here. That's fine. Use what you are given. Okay, so here we are going to use first our equation of state, or an ideal gas. There it is. Volume is equal to N times R times T. This, of course, is number of moles times the gas constant times temperature divided by pressure. Okay, so we plug all these values in, and we get 1.71 times 10 to the negative 2 meters cubed. And if we stopped there, that would be a very bad idea, because we're specifically instructed to give centimeters cubed. So make sure you read carefully, guys. All right. Okay, so then our conversion factor is determined simply by taking 1 meter times 1 meter, and that is 100 centimeters times 100 centimeters, and that's going to give us then 10 to the 4 centimeters squared. Note that this is always an easy way to do a conversion if you're not sure what the conversion factor is. So for example, this is not given in the data booklet, but if I know that 1 meter is equal to 100 centimeters, then it's quite an easy calculation, and I can do this with cubic meters. It would also be easy to convert meters to millimeters. It's just an easy way to go about it. Okay, so my final answer then will be 1.71 times 10 to the 2 centimeters cubed. All right, what is the molar mass of oxygen? We've already calculated this, so no reason to dwell. B, what volume will be occupied by 1.0 kilograms of oxygen at 25 degrees Celsius? And 1.3 times 10 to the 5 pascals. Okay, so first we convert 1 kilogram to moles. And our next step then will be to convert our temperature to Kelvin. Remember, always be using Kelvin, Buck. Our volume, we determined by simply plugging our values into a slightly rearranged universal gas law equation. And our answer then is 0.6 meters cubed. So there you go. So for 51, here is where we use a very handy shortcut that I showed you in a previous lecture. A container has some gas at twice atmospheric pressure. Volume is reduced, temperature is the same. You are asked to find the new pressure. Okay, so we use this equation, which you have seen before, where initial conditions are equal to final conditions. Since temperature is constant, it cancels out of the equation, simplifying our math nicely. And we simply rearrange the equation and solve for the variable that we want, which in this case is final pressure. Okay, so we then multiply initial pressure by the ratio of volume. Okay, so we have here initial volume divided by our final volume. Okay, and we find that our answer is 2.51 times 10 to the 5 pascals. Pressure is increased because pressure is inversely proportionate to volume, where temperature is constant. And this is one of our key concepts from a previous lecture as well. Okay, next one, very similar mathematics, except this time we also have a temperature increase. Normally this would be a problem, but with this equation, it's not a problem at all. We have 5 of the 6 variables that we need. So we just plug all 5 of those variables in after carefully defining them. And we pop them into the equation, and we find that we have 1.7 meters cubed. Conveniently, our units are going to cancel out when we plug them in, so you don't really have to write either Kelvin or pressure if you don't want to. They're just going to cancel out. Don't waste your time. Okay, 55. Similar manipulation of our universal gas law equation. Here pressure is constant, and we're asked to find the final temperature. So define our variables. Pressure cancels out. We solve for the variable we want, which in this case is final temperature. And that will be equal to initial temperature times the ratio of final volume divided by initial volume. Note that this is a very popular kind of setup for paper 1 questions. So just be aware that you may see these again. Our final step is to convert Kelvin to degrees Celsius by subtracting 273 from our value. Note that this would be another easy way to catch you off your guard in a paper 1 question. And so you would definitely predict that examiners would put 580 degrees Celsius on a test question because they're extremely mean and they're trying to trip you up and making sure that you are indeed reading questions carefully. Okay, that does it here. I am Mr. Van Lowe. Again, do not click subscribe. I'm not trying to monetize YouTube, for sure. Okay, have a great day, guys. Talk to you later.